Today we have a special seminar by the Dr. Hwanwoo Kim, who is currently doing the postdoctor at the Duke University. Today I think we will talk about some optimization we typically use for our model development. So hopefully, after seminar, we will have a lunch together, and then maybe I will specify some couple people, and maybe you can show your recent results so that hopefully you can do something together. Okay, so yeah, let's welcome Dr. Kim.
Thank you for the introduction. As Professor Kim said, I'm currently doing a postdoc at Duke in statistical science department. So today I'm going to talk about how to utilize Gaussian process for developing an optimization algorithm, as well as an uncertainty quantification tool. And there's a lot of jargon here, but I'm going to clarify one by one as the slide goes on. So before I start, like, how many of you guys are familiar with the Gaussian process?
Gaussian process?
I mean, I'm going to start from scratch, but I just want to get some sense. And later, I might assume a bit of knowledge in Bayesian statistics, but let's see how it goes. Okay, so here's the outline. I'm going to introduce what Gaussian process is. Of course, this topic it takes a whole semester to learn, but I will try to make it as short as possible. And based on the Gaussian process, I will going to introduce this optimization strategy, often known as Bayesian optimization, which is very popular in deep learning hyperparameter tuning. I'm going to introduce some theoretical results and as well as how to improve those existing algorithms. And after that, I will move on to uncertainty quantification tasks. And this is perhaps where some of the scientists here might be interested in, because I will use this introduced methods to estimate the parameters of differential equations, as well as how to quantify uncertainties associated with it. So let's first start with the Gaussian process. So in just basic introductory probability class, we often deal with a random variable. It could be binary, or it could be integer valued, it could be real valued, but today I'm going to focus on a random variable whose value is a function, okay? And if you know about the stochastic process, we already know this random variable because stochastic process is basically a random variable that takes a function. Why? Because this index could be viewed as an input for the function. So by doing this index as an input, we're going to view the stochastic process as a random function, okay? And one particular random function that is very popular in machine learning and even in statistics and science is Gaussian process. So this is basically an analog of Gaussian distribution, which often, you guys learned in the probability theory class, but we're going to lift it into the space of functions. This is Gaussian process, so it has a mean and the covariance kernel. So mean function is exactly same as just the typical mean in the Gaussian distribution. Because this random variable is a function, takes a value in the function space. Of course, it's centered around some mean function mu, and there is a covariance kernel k. This will gonna tell you the covariance between the function elements, but it's actually richer than just the covariance. It governs all these sample pass properties. So the Gaussian process is a distribution over the space of continuous functions, and typically people use this notation F distributed according to GP with center mu, the center mean function mu, and the covariance kernel k. So here are some random draws from the GP Gaussian process centered at 0, with a covariance kernel known as exponential kernel, which I'm going to introduce soon. So these are just the random draws, 5 random draws, and blue one is just the center of that function. I mean the random variable. Okay, is so far so good. So nice thing about Gaussian process is that you can actually derive a posterior distribution. So given a data, which is simply a function evaluation. So what we do is we're going to put a Gaussian process onto a function f that we don't know, and we're going to update our prior based on these evaluations that we make, which is the data. And nice thing is that we can derive a posterior mean and the posterior variance in a closed form. So this posterior mean is simply this KT and KTT are all some kernels evaluated at some locations. So by the way, kernels, the covariance kernel I introduced at the beginning takes 2 elements, and this kernel KT, this KT at the front of the posterior mean, that's simply a vector where the one element is fixed as an input data, and the rest of the inputs are the one that comes from the data dt there. And KTT is simply just a covariance kernel matrix where each ij's elements are evaluated through the data given over there dt. So using all these elements that we already know, by the way, FT is the collection of all the function evaluations. So given all these data we have, we can update our prior and derive the posterior. So this posterior is now, we have a new center on this function space, and that actually you can show that this precisely interpolates all the data because that's what that's where the functions are observed. And these posterior variance quantifies uncertainty associated that posterior mean. So let's just schematically see how this works. Okay, so the previous plot, so the left plot is where I put the Gaussian process prior onto this red function. So red dotted function is something that we do not know. At first, we just put a 0 mean and the covariance kernel given here at the bottom, square exponential kernel. So this is one example. And another example is the Matern kernel. You don't need to know those complicated equation. But if you use square exponential kernel, this was the prior. And after making observations on these red dots, what I have explained before was you can compute this posterior mean and variance, right? So the posterior mean now, this blue curve, passes on these red dots. And actually, the uncertainties of this posterior mean has been quite substantially shrunken in the region near these red dots, which demonstrates how good these approximation is. But still, in the region where you don't observe the data, the uncertainties are quite large. So these blue shaded regions are basically the posterior mean, this mu t, plus minus 1.96 of the posterior variance, which quantifies how good these estimations or approximations are. So basically, the upshot is that this Gaussian process provides a nice way to approximate some unknown function, even when you just have some partial information about the function, namely, you only have some observations. And the observations intuitively this makes sense because where the observations are not made, you have high uncertainty. So this will be used throughout the talk when I develop the optimization algorithm as well as the subsequent uncertainty quantification. So I hope this gives a nice overview of the Gaussian process. And of course, there's a bunch of theories that are developed. But that's enough for this talk. So now I'm going to talk about how to utilize that tool to develop a black box optimization. Okay, so this optimization is slightly different or somewhat different from perhaps if you go to take optimization class in university, because I'm going to optimize a function f. So f is defined over some search space, which is compact. or typically you could just think it as a rectangle, hyper rectangle. The difference comes in from the second bullet point. So f, the function f, the only thing that we know about f is that we can evaluate this function. Okay, so if you go take an optimization class, often they require a gradient or Hessian information about f if you want to optimize, because that's where you want to, I mean, that determines the next iteration. But right now, all I assume is that f is only evaluatable, and these evaluation locations, I'm going to denote it as capital theta T, and also the collection of evaluations at capital F sub T. And also, the typical applications of this kind of problem comes from this large scale neural network model tuning, as well as computer model calibration, and also some maximum a posterior estimates for intractable likelihood. So I'm gonna demonstrate this Bayesian optimization in the second and the last example. But you can actually go find, if you go search Bayesian optimization in Google, the first like hyperparameter tuning for neural network models are actually the most widely used application for this type of algorithm that I'm going to introduce. So all these algorithms has additional characteristic that the function f is very expensive to evaluate. So we're going to carefully choose where to evaluate that f, but we're going to reach the optimum as soon as possible. And that's the goal of the Bayesian optimization. And this is one particular instance of Bayesian optimization known as Gaussian process upper confidence bound. So the way it works is, so you need to first specify all the things that you need to develop Gaussian process. You need to specify kernel, and you specify some total number of iterations that you're going to run the algorithm. And say you have initial query locations and initial observations of the function. And first compute the posterior mean and variance, like I did at the beginning of the talk. So here you just compute these two quantities. That's gonna give us some nice function approximation like this, right? But we're not gonna have as much data as that. We're gonna have a few data, but we still build this posterior mean and variance. And after that, we're gonna carefully select where to evaluate this function in the next time. So we're gonna find that location by maximizing this optimization objective known as acquisition function, or in this case, this is known as upper confidence bound function, which is simply posterior mean plus some constant times posterior standard deviation. So the intuition is that we know that this first part serves as a good approximation of the objective function. So by finding the optimum of this first part, we're gonna get close to the optimum of the objective function. But this is only gonna be true when t is sufficiently large such that optimum agrees. So at the beginning, we would like to reduce the uncertainty of this objective function at the surrogate mu, right? The approximation mu. So the way we do this is at the beginning, we're gonna actually find an optimum or maximum that maximizes this posterior standard deviation. The reason is by finding a region where posterior standard deviation is large, we're gonna find where this approximation is the poorest. So if you look at this plot, it's basically finding a region where this posterior band is large. I mean, the widths of these intervals are large. So by balancing these two goals, people came up with this acquisition function. So the way it works is at the beginning, you're going to reduce the uncertainty by finding this maximum of posterior standard deviation. After you have shrunken the posterior standard deviation sufficiently, this term will be almost negligible, and then you're going to find the maximum of the posterior mean. And that's going to lead us to optimum that's close to the optimum of the target objective. So you just iterate this. At each iteration, you're going to find the maximizer of this function. You supplement it to the existing function evaluation set, and then you keep iterate. So at each iteration, you're gonna keep update posterior mean and variance. So let me just graphically demonstrate this. This is actually the same function that you have seen, but I'm gonna assume that you have two data at first. Okay. Actually, yeah, sorry, three data. So here, the red dotted curve is the true objective function we would like to optimize. And these three red dots are the function evaluations that we know. So we're gonna build a posterior mean. That's the blue curve that passes over those data. That should serve as an approximation to this red dotted curve. And you can see also where the uncertainty is large about that blue curve. So after you build this posterior mean and variance, what you do is you're gonna find a point which maximizes this acquisition function, which was posterior mean plus the posterior standard deviation. It seems like it's somewhere here, right? So that's this red dot is where you evaluate the function next. So you make an evaluation and you update the posterior mean. This is the second posterior mean at the second iteration. So you now get a better approximation, and you do the same. Now the posterior mean plus posterior standard deviation is highest at the left end points. You make a function evaluations at that point. You update it, and you just keep iterate. So at the beginning, what happens is you're going to explore the region you haven't explored, so that the posterior mean is gets closer to the target red function, and you just iterate this. And what happens after you sufficiently reduce the uncertainty? So you see that these bands get shrunken as you make more evaluations, right? After you have made sufficient after this reduction of uncertainty is sufficient. What happens is these algorithm will tend to explore the region of optimum more extensively. So look at the left end mode of the red function. So it's previously we only had 2 points, but we added this additional red points that's because that's where acquisition function is maximized. And as the iteration goes on, the algorithm will gonna continuously explore the region of this so that it eventually hits the maximum of the function. Okay, so this is how the algorithm works.
Just from the whole domain.
Yeah.
The acquisition function tell that point is we need the next step observation.
So yes, so here at the beginning, acquisition function does not really tell you where the optimum is, but then because this blue curve, right, posterior mean, that's getting closer to this red curve. So the acquisition function later tells you where the optimum is. Right? So if you just look at the acquisition function, at the beginning, it's not really informative where the optimum is. It's more informative about where the uncertainty is large. But as time goes on, the uncertainty has been sufficiently shrunken. This acquisition function actually gets the geometry of the original function. So optimum is also can be found by maximizing the acquisition function.
It's not just finding the point where the uncertainty is just high.
So yeah, so that's at the beginning, uncertainty is our focus, but later we want to exploit this structure and we find the optimum of the acquisition function, and that's gonna lead us to the optimum.
Yeah, acquisition function was summation of the mean and standard deviation.
Yes. Yeah, that's what.
Yeah. So try to both find the point that
Yeah.
not only the mean value,
Yeah,
but also
exactly.
the uncertainty.
Yeah.
I see.
Can I know the meaning of beta T? Why that?
So beta T actually essentially controls how you want to put more weight on uncertainty reduction and finding the maximization.
So do we need to specify beta T here or?
Yes, so typically you would choose beta T. In practice, it's actually very difficult to tune. People just use some constant value,
Wow.
because at the beginning, uncertainty is quite large, no matter what, problem is. Because you typically put zero meaning Gaussian process, uncertainty hasn't been reduced. So the way it works is it's gonna find a point that maximizes this so that you reduce the uncertainty, but later it's gonna focus on this. But to actually get the good convergence rate, you need to tune this very carefully. Because this will tell you how much time or effort you put on this uncertainty reduction over the maximization.
So maybe we can put it in some
Yeah.
decreasing function.
Yes.
Like, 10.
Or I mean, actually, so in many optimization, I think step size is chosen to be decreasing, but in Bayesian optimization, unfortunately, a lot of theory tells you actually beta t is increasing somehow. Because you need to later, because this is not just for convex optimization, it's non-convex, so optimum could happen anywhere. So you need to have sufficient like exploration. And the convergence guarantee is only met when you increase beta t so that you don't miss any local optimum.
Okay, so when is that to run away from the
Yeah. Yeah. Any other question? So that's just a pictorial depiction of the algorithm, and it actually serves as a good tool. I mean, perhaps nice tool for optimizing a non-convex optimization problems. As you see, all I required is just a function evaluations, nothing about gradient or Hessian. And you don't even need to know the functional form of the objective function. So let's just delve into a bit of theory, how like people have developed the theory. So there are two widely used notions in understanding the performance of these type of algorithms. First, known as cumulative regret, which basically sums up over all the differences between the maximum and the current evaluation. Second metric, simple regret, is perhaps more relevant for optimization tasks, which simply compares the optimum value, the maximum, with the best function evaluation you have so far. So as long as simple regret converges to zero, the algorithm is demonstrating the convergence, right? So what people have shown is by utilizing this third bullet point, so average cumulative regret is simply just dividing this cumulative regret by total number of this iteration capital T, that bounds the simple regret, and people establish a sublinear growth of this cumulative regret. So if RT is sublinear, this average cumulative regret will gonna go to zero, and that's gonna lead to the convergence of the simple regret, because simple regret will be also go to zero. And yeah, so that's one way to establish, and some other people actually directly tackle this simple regret convergence. And here are some existing results. So let me just parse these things a bit. So you first the reproducible kernel Hilbert space assumption. So to put it simply, this assumption is basically saying that the objective function f that we want to optimize, right, could be expressed as a linear combination of these kernels. Okay, so if you fix one argument, right, which will be our data, this could be viewed as a function with respect to the first argument. What that RKHS assumption is simply the objective function could be expressed roughly as a linear combination of these, like either this matern kernel or square exponential kernel. Okay, so this is why the kernel matters. For when you say when you want to optimize a function, you need to carefully choose kernel, because each kernel will gonna, I mean, the properties of the kernel will be reflected on the function that you want to approximate. So for instance, square exponential kernel is often used for objective functions that are infinitely differentiable, smooth functions. Matern kernels are typically used for functions that are that has finite order of differentiability. And this parameter nu essentially tells you how much differentiability that the objective function has. Okay. So under such assumption, and if you use the UCB algorithm that I introduced here with beta t selected to be some norm of the function f, which of course you cannot know in advance, but this is just for theory. If you set it like that, you can show that this cumulative regret grows at a following rate, okay? So let's parse it down. Let's first focus on square exponential kernel. It grows like a square root of t, right? You can first neglect this logarithmic order because this square root of t will gonna dominate as t gets large. But this logarithmic order tells you where the dimensionality gets in, right? So as the search space dimension gets larger, so when you perform high dimensional optimization, the rate's gonna suffer, which makes sense, right? So if you perform optimization in high dimensional, it's gonna be much more difficult. So that's where this dimensionality of the search space kicks in. But also, these type of analysis also reflects the structure of the function, where the definition smoothness actually kicks in as well. So if you look at Matern kernel, there is a smoothness parameter nu, which I told you that it determines how much differentiability the objective function has. So nu, if nu is large, that means the function is highly smooth. And as you can see, if nu gets large, this leading term matches, right? But for small nu, it's actually the rate suffers because this will be almost like a linear. And of course, the convergence will be slower. So the upshot is that if you want to optimize a smooth function, you're gonna have a faster rate. But if you want to optimize a function in a high dimensional space, you're gonna suffer the rate, right? So that was the one result established by this person, Liu, which was expressed in terms of the cumulative regret for this particular GPUCB algorithm. But there's alternative, there's another type of convergence rate analysis this established by Bull, actually earlier than that paper, which just directly tackles the simple regret and show that the optimal convergence rate of these type of algorithms is key to the minus nu over d, where nu was the smoothness parameter and d was the dimension. So this is the optimal rate if you use the Matern kernel. So let's parse it again. D was the dimension. So if d is large, the rate is going to be slower. Nu is the smoothness. So this governs how smooth the objective function is. So for highly smooth function, nu is large, so the convergence rate is faster. And this Adam Bull in 2011, what he has shown is that no matter what strategy you use, so when I say strategy, it means a strategy to select this data type. So here I introduced this GPUCB, which is one particular strategy to pick this next point. But there's a lot of different versions of Bayesian optimization. And what Adam Bull in 2011 paper shown is that no matter what strategy you pick, this is the optimal convergence rate. So there's a bit of gap between the current existing algorithm, which are popular with the optimal convergence rate. So as you can see, if you divide this, right, the first line by the capital T, even if you ignore the logarithmic term, if you divide the leading term by capital T, it's still slower than this optimal convergence rate. So how can we make how can we modify the existing algorithm so that we can match this convergence rate in theory? There's a very nice trick. One slight modification that I make is that let's just go back to the GPUCV. The rest of them are exactly the same. You just compute the mean and variance, posterior mean and variance, get the next point, right? Forget about this exploit plus. What I do is that if you just randomly sample from the search space, so P is some probability distribution defined on the search space. Typically, it's going to be uniform. If you just randomly select a point from that search space and add it to all these evaluation locations and function evaluations, so at each iteration, you're going to evaluate the function twice, and then you update it accordingly. This is what I call GPUCV plus. So basically, there are 2 points that I evaluate function. One was the typical UCV points that's selected by this. That's the points that's obtained by maximizing this mean and mean plus variance standard deviation. The other point is just randomly selected points. So this addition of random selected points, we're gonna add additional layer of exploration. So this will gonna allow us to explore the search space, wider search space, so that we can build a better surrogate or better approximation in a faster sense. And so this is what I call GPUCV plus. And if you just forget about this posterior standard deviation term that was included in previous UCV function, but still let's just rather find an optimizer of the posterior mean and then explore the search space through this random sample point. That's a strategy I call exploit plus. And just that simple modification actually leads to quite improvement in terms of the theory. So in expectation, what I can show is that simple regret, if you use maternal, is capital T to the minus nu over D plus some epsilon that could be arbitrarily small. And for square exponential kernel, you can actually show that the convergence rate is at an exponential rate. So in expectation. So such small modification actually makes quite a bit of improvement in terms of the theory. So here's a demonstration of optimizing this nasty non-convex function known as Ackley function, often used for test problem. So this is a 2-dimensional depiction of the Ackley function that I described in the first one, the line above, right? This function could be defined in arbitrary dimension D, but here I just used D equal to 2. So as you can see, there's tons of local optimum, but there's one global the minimum. And let's compare the performance. So GPUCV was the one I introduced at the beginning to motivate the top. And exploit plus and GPUCV plus were the modifications I made. And EI is expected improvement and probability of improvement that I haven't explained in this talk, but those 2 are also popular Bayesian optimization strategy. So as you can see, the more we make function evaluations, all these algorithms tend to get closer to the optimum, but the simple modification seems to dramatically improve the existing algorithms, right? And in fact, if you look at this GPUCV plus, it's quite surprising how, given such nasty structure, the algorithm performs quite well, even in the 10-dimensional case. So the optimum should be, because we are measuring the performance in terms of the simple regret, if it hits 0, that's gonna tell you the convergence, but of course, a lot of convergences are in asymptotic sense. So this seems to indicate that the performance is quite good. So that's just one test example. And here's as I said, I can also use this type of algorithms for computer simulation parameter tuning. So here's one example where you want to say design a garden sprinkler, right? So you need to tune all these parameters like nose angle and diameter of the sprinkler head. So these are often requested by industrial engineers, and they have some kind of computer simulation software whose mathematical expression is not known, but you can just provide inputs of these parameters, and then it's going to spit out how large the garden sprinkler can water. And here's another demonstration of these type of algorithms, okay, the performance. So all these 6 algorithms seems to find the maximum as the iteration or as more observations has been made. So actually the maximum is around like 20. So if you make more observations, it's gonna eventually hit the maximum. It's gonna eventually find the parameter configuration that maximizes the sprinkler range. Okay, so these two are just a demonstration. So perhaps now this is where some of the scientists might be interested in, because I'm gonna now use this for estimating parameters of the differential equation, right? So before I start, any questions?
Very expensive. I think a lot depends on how to define.
Yes, so that matters when, so you need to have some kind of information about the objective function. Say like if your objective is smooth function, right? You would use like square exponential kernel. But if you have a like say much rougher function, typically people go with maternal kernel and with a very small new value. Okay, because if you use small new value, the function space generated by those maternal kernel would tend to be larger. But it's going to take more data to actually to get a good performance.
Another question is that so your GPU UCB,
Yes.
that the key idea is sampling one more point.
Yeah, so it's actually the key idea is just to explore more, right?
Okay.
Because here previously we explored and maximized at the same time, right? But what I'm proposing is let's explore more so that we can get a faster convergence rate, because this is often used for non-convex optimization. So you want to explore as much as you could. So you need to first reduce, the candidates of the optimum. So this type of exploration will gonna lead us to better this posterior mean approximation.
So then have you tried any other distribution for sampling or other methods?
This one is typically for, it's the Bayesian optimization is often used in the hyper rectangle. So people often, what I propose is just a uniform because it's very easy to sample, but you can technically pick any distribution which has a positive density on that region. If you pick other samplers, you might have to think about like the computational cost of it. So yeah. So now let's use this to estimate the parameters of the differential equations. So let me motivate using very naive mathematical biology example. So here's a typical data. The data that's typical for local Volterra model. So legs and hair, those are the type of like a rabbit and the fox. So these are the population over 1900 to 1920. So as you see these dots, so these red dots are the hair. These are the population level observed at these years, and links also are observed at these even number of years. And we want to find a differential equation model that explains this data, right? And one widely used differential equation model is this local Volterra. But it depends on what type of parameter you choose, right? This parameter, alpha, beta, delta, gamma, right? Those are the parameters that actually exhibits a physical meaning. And X and Y are the population dynamics. So X, that's gonna be the hair population. I mean, that's gonna encode hair population over time, T. And Y, that's gonna be lynx population over time T. And we want to describe such data using this type of differential equation model. So here are two different examples, two different solution trajectory of differential equation that I've just shown you based on different parameter value. So the top rows, those are solution trajectory of this local Volterra model based on very well chosen alpha, beta, delta, gamma value. Okay, so if you choose those well, you see that the solution clearly, I mean, quite matches with the data, right? So this type of model, we're going to depict the population dynamics quite well with a physical interpretation. But if you don't calibrate those parameters well, you see these solutions are drastically off from the data, right? So how can we actually get those parameters, accurate parameters, so that we can utilize this type of differential equation models on the data we have, right? So this could be formulated into optimization problem, right? So the parameters are alpha, beta, delta, gamma, and for each alpha, beta, delta, gamma, you're going to have solution of ODE, right? The solution of dx dt and dy dt there, and you can simply formulate this into an optimization problem by simply taking the square of the sum of the differences, right? So you just evaluate the solution at the case time point and compare it with the data point xk. So xtk is this blue curve at time tk, and the xk is the blue dotted points. You simply compare and take the difference and square it and add both for lengths and hair, and you find the parameter configuration that maximizes this negative sum of squares, right? So if you do that, you're going to find a parameter that best matches with the data, right? You could also formulate it into a much more complicated case where you don't have complete observation over of the data over the whole region from 1900 to 1920, but say you only have a summary, right? So instead of observing these red dots over all these years, what you could have is you could just have an average of the hair population over the region 1900 to 1920, or lynx population from 1900 to 1920, right? That makes problem much harder. And I'm gonna just use this a bit of perhaps convoluted notation. So G, this is simply a mapping from the solution to some summary, okay? So G could be just, think it as, I mean, naively, you could think it as a averaging operator, or you could just, but you could just pretty much use any kind of lower dimensional summary. A function that generates lower dimensional summary. And then you can just compare that with the observation. So depending on the type of data you have, you could formulate this into an optimization problem, and the Bayesian optimization will gonna allow us to find the parameter data that best matches with the data, because we don't need to know the functional form, right? Note that xt and yt in our setup does not have closed form solution, right? It's just a solution of the ODE. And if you consider like many different ODEs, oftentimes the solutions cannot be expressed in terms of the closed form expression, right? So you have to numerically simulate or solve the ODE, but the Bayesian optimization, good thing about it is you only need to evaluate, right? So let's use Bayesian optimization, and you can actually solve for good parameter value, but we want to do something more, right? We want to do a uncertainty quantification on this point estimates. So these type of objective functions that I just introduced involves a solution of the ODE, which is very expensive, which could be, right? The example that I've shown you is very simple, but as the model gets more complicated, this can be very, very expensive. So we would like to evaluate as few as possible, but we want to get the good parameter value. So Bayesian optimization naturally serves a good candidate, but it doesn't provide an uncertainty quantification tool, right? So which I'm gonna address soon. But I'm gonna just say like two more advantages, like why it suits for Bayesian optimization, because oftentimes this objective function could be highly non-convex. So all these characteristics of the aforementioned objective function serves as a good candidate for Bayesian optimization application. And now let's just, as I said, do uncertainty quantification as well. So now suppose the data are actually corrupted by some random nodes, right? So previously, we had these data, right? Of course, these data will be slightly different from the solution. So let's assume that this deviances, right? The difference between the solution trajectory and the data as some kind of random error, right? You could think it as a Gaussian, random error or some other random error, but for this talk, let's just focus on Gaussian random error. And if you think it, impose such assumption, you can actually get a likelihood, right? What's known as likelihood function, because this random error, right, we're gonna induce the distribution of the data. So here I'm using it as a summary, this G as a summary operator. So G could be, if G is identity, this simply comes back to the way I explained. So it's simply just the trajectory plus some random noise. But if G is like say averaging, it's also like the average of the trajectory plus some random noise. We are assuming that's simply the observation, which is average of the link's population over some time period. So if you just make such assumption, these objective function that I described here could be viewed as a log likelihood, right? Because this log of the data distribution is exactly of this form because of this Gaussian distribution assumption. So let's do the Bayesian inference. So Bayesian inference simply can be done by, the central object of the Bayesian inference is the posterior distribution. So how can we characterize the posterior distribution? So posterior distribution is simply proportional to the prior you put times the likelihood. We actually already talked about the likelihood before. Prior here, this is where the domain knowledge comes in, right? So if you have more extensive knowledge about how to utilize this type of models, you can base such information in prior. And then since you have this likelihood, you can now characterize the posterior, right? So let's use such characterization for doing uncertainty quantification. So log likelihood, right? This one is simply as you got it from the this objective formulation, and log prior. This is where the prior knowledge gets in, and you can now get the unnormalized log posterior by simply adding the log likelihood and log prior. And the reason why we are using this unnormalized log posterior is oftentimes in Bayesian inference, the posterior distribution is intractable in the sense that the normalizing constant is not known. We can only characterize this posterior distribution that I just described here, right? This needs to sum to 1, but oftentimes this normalizing constant is ridiculously hard to compute. So people just characterize this posterior distribution using up to some constant, and that's exactly the set, right? And that's oftentimes enough depending on the goal. So if you want to just get the map estimate, which is just a point estimate for the parameter, that's simply the maximizer of this unnormalized log posterior, because whether you take the log or not, the maximum is still the same. So here, you simply use Bayesian optimization to get the map estimate. And now, say you want to do the uncertainty quantification, you are doing a posterior approximation. So our posterior was proportional to exponential of f theta. And if we use Gaussian process surrogate, namely the Gaussian process mean, we can actually approximate this exponential of f theta by exponential of posterior mean, right? So this, because we are creating a Gaussian process as a surrogate for the objective function f, we also naturally have this posterior approximation up to some constant. Okay. So the reason why, so we need to now construct this posterior mean, right, carefully to get a good approximation. And I propose that we could just use the same optimization algorithm that I introduced. The reason is that why like such optimization like algorithm leads to good approximation, because optimization algorithm itself is an algorithm that generates a points near the region of maximum, right? So this is typically the region where we care mostly about posterior distribution. And by using optimization algorithms nature, we are putting more efforts in understanding the region of the maximum. So thereby we are building an approximation or surrogate that's close in the region of posterior mode. But at the same time, the additional random exploration step guarantees or make sure that the posterior approximation is good in a global sense, that it captures overall shape of the posterior density. So this two aspects is why I'm using this optimization algorithm that I introduced as a way to also get a posterior approximation. And you can establish some kind of, Hellinger distance like a bounds. And let's now demonstrate this in like one dynamical system example, three-dimensional dynamical system where, where the data is simply so we're gonna suppose there's a true parameter data star, and the data is simply data star mapped under this function g. G is simply the average of the solution of the first and the second moment. So this x, the bold-face xt, is solution of this the dynamical system differential equation, and you take the average over t naught to t, and we're gonna, of course, these the solution depends on the data. So I'm gonna just generate a data from the data star and add some random noise. Of course, these are all synthetic example, and here's one concrete example for Rossler dynamics. Say you want to estimate the parameters of data, and we're gonna put a prior, right? Because we want to do the Bayesian inference, we're gonna put a prior on data, and I'm gonna put a prior that has positive mass on the between 1 to 14. Suppose data was generated with 5.7, so I'm just solving this equation with data plugged in with 5.7 and took the average, the solution over the time window 20 to 50, impose the Gaussian prior, and here's an objective function, right? So of course here the objective function is actually non-convex, but it's quite hard to see. So this black curve is the true objective function. So the prior, so this objective function is a log posterior. So the maximum is going to be the posterior mode. And all these three different colors represents our posterior mean approximation. So random, this green color posterior approximation is simply a Gaussian process mean where the points were randomly selected, and GPUCB is the Gaussian process mean where the points were just selected by GPUCB algorithm, versus these exploit plus and GPUCB plus algorithms are where these posterior mean are constructed using both UCB and the random explorations that I added. So all four the surrogates closely approximates this black curve. But you see some distinctive features, right? GPUCV tends to focus a lot on this region of mode. So that's where the maximum of the log posterior is. But it actually doesn't capture the region outside of region outside of the maximum. Because optimization algorithm is often used for probing the region of the optimum, but it doesn't care anything about the outside of the optimum. And random exploration, on the other hand, I mean, because this is one-dimensional example, it seems like it's approximating everywhere quite well. But if you look at the region where these red dots are concentrated, the green curve is slightly off from the other three curves. So that's the disadvantage of random exploration, because it doesn't capture this accurateness in the region of where the posterior mode is, while the other two algorithms seems to balance the goal of UCB and the random exploration version. So you see those in actually this histogram of selected points. So as you see, the blue this blue histogram represents the selected points by UCB. So as you see, the optimum is somewhere in between 6 and 8, and it tends to focus too much on the selecting points on the maximum. So that's where UCB puts most of effort, while random just distributes its design points everywhere. The design points is the points that you select to construct this posterior approximation, while these two algorithms are balancing those two. So if you look at now posterior approximation, so black curve is the true posterior distribution that you could get in this example. So here the prior was given, the Gaussian 6 with standard deviation 2. And likelihood, you can also, evaluate it by solving this differential equation over the region of the grid. And you can also, this black curve is obtained by MCMC. And all these four figures now represents the histograms of the samples you could obtain from each of the approximated posterior. So black is the true. The colored one is approximation, and as you can see, if you just use UCB points to build a Gaussian process to approximate this posterior, it's quite accurate in detecting or finding where the local maximum is, but it doesn't capture the global geometry, right? So here there's a lot of probably density that are missed by this histogram. On the other hand, random exploration does not really capture where the optimum is. So it's each of them are insufficient in different reasons, while UCB plus and exploit plus seems to balance those. And another example of lost runs 363. This is now for a three-dimensional example, and this is where more clear demonstration where random exploration fails. So here, all these approximation, right? So this true, these gray colored histograms are the samples of the posterior distribution, the true posterior distribution. But if you use now Gaussian process surrogate or Gaussian process mean-based posterior approximation using this random sample points, all these approximations tend to be off. Of course, if you make more, if you make more data, if you observe more data, here I only used 400 data to construct this approximation. But if you make say 1,000, 2,000, the accuracy will gonna improve. But given the number of the observations you make, you can actually significantly improve using this the algorithms that I introduced even for posterior approximation. Right, so here UCB now you can see that it tends to capture the local mode quite well, but because it concentrates too much on the local mode, the posterior approximation, the geometry often get distorted. So those are the demonstration of the uncertainty quantification, and here is the references, and I'm happy to take questions. Yeah, thank you.
Yeah, any questions, please feel free to.
Thank you. When you choose the prior, so for instance, for the Resler system, should you know the given data zeta star? I mean, it seems like prior is chosen.
Prior here, I just arbitrarily chose for this because this is synthetic example.
Yeah.
In real world, I believe those should be chosen based on the domain knowledge, and the data will be baked into the likelihood.
So should we choose the prior very carefully, or?
Yes, because oftentimes, depending on how you pick this data, the solution solution might explode. I mean, even for Rosler dynamics, this is very sensitive to the parameter value. Yeah. So you are gonna have like very different trajectory. Yeah. I mean, often in experience, I had tons of like numerical instability coming from like if you don't select the search space close to the meaningful data value.
Okay.
I heard that when people choose the design form, the method called the Latin hybrid method. So is there any advantages?
Yeah, so the reason, that's a good point. So Latin hypercube is a point that's spread it well enough on the search space so that like roughly speaking, if you just narrow to one particular bin, there's always one point. The reason why such kind of design points is not good for this example is that it's focused purely on the space feeling, so it tends to spread it, evenly on the search space. But if you do not put much effort on the region of optimum, it's gonna have same, disadvantage as the random selected points. It's not gonna be accurate in depicting the region of local mode.
And my intuition, this method is so. For this method, the point is that we want the mean trajectory will approximate the original stereo distribution. Then I think it could be much better to choose the point where only the variance
is large.
because that means at
So
that point
what you're saying is if I just pick a point that's found by neglecting this term.
right. I think that could be much better than considering. Of course, we should. We want to concentrate on the roads.
Yeah.
But maybe we just want to make this mean trajectory well consider distribution, and we need to reduce the variance as much as possible, rather than focusing on the maximum.
I partially agree because if you neglect this part, what happens is UCB algorithms will gonna just explore everywhere, not just on the modes. Like for instance, at the beginning, the prior is like brackets. Here, it's gonna, regardless where optimum is, it's just gonna find any points, right? So actually what happens with, if you just optimize this part, right?
Yeah.
That's, in my understanding, initially that's gonna be almost same as just random sample.
Any other questions, please?
So in your examples, you choose chaotic systems.
Yeah.
So I wonder whether chaoticity helps your inference or did you just choose?
Honestly, in my, honestly speaking, I think it was really hard to deal with chaotic dynamical system because, if you don't set the parameter values, as I said, like the range of the parameter values, like well enough, oftentimes like the likelihood function just blows up and it's not even defined.
Yeah.
So yeah, I mean, honestly speaking, I don't, at least for me, the chaoticity didn't really help.
If you don't have a question, for your project, do you think using this approach is better? Or keep using your own current approach is better? Just think about this in this room, half of you guys doing parameter estimation. What's the pros and cons?
I want to test it, but at least, so I'm doing
your
parameter, yeah, parameter optimization. My sleep locked in this position. But maybe that takes some time because we need to solve different things.
So
Maybe we could,
why this approach could be better than what we're doing?
so only for reduce the competition. That is the only point.
Speed up.
And speed up. And maybe they could also provide much better way to approximate the confidence interval because my current approach just rely on the bootstrapping. So we could provide much reliable confidence interval.
Who else? Think about it. Working the parameter after reading and then coming. Then what else do? I'll go with the yes. What do you think? Compared to our own Bayesian friends. So key point is we're focusing on the some modes so that maybe we can reach to the maximum to speed up. What could be disadvantage then? Is there any concern you have?
If the dynamics is so for my case, I use some switch like dynamics. In that case,
Stiffness in the dynamics.
maybe the loss function itself could be very nasty structure. Yeah, in that case, it's not okay. But I want to try.
Okay, good. So this algorithm is publicly available now or going more?
It's actually under review.
Under review.
Well, I mean, UCB is very widely used. It's, I think if you just implement with the Gaussian process package, it's quite simple. Yeah, and even like the computation here just involves like matrix vector products. And the only thing that perhaps needs a bit of tuning is this this part, right? Where you want to optimize for the acquisition function. People just use quasi-Newton or like SGD. And even if you don't get the exact solution, you can, I mean, actually in theory, you can also prove the convergence, even if you don't have, yeah, even if you don't solve this second step exactly.
So any question? You have something? Yeah. If not, yeah, because you look at me, so no, okay, so after seminar we will have a lunch, but during the lunch time, For those who want to have individual meeting with Dr. Kim, let me know. Maybe please let the Dr. Song know. So that maybe you can order the meeting schedule, and then maybe after the lunch you can have about 10 or 15-minute individual meeting. Maybe you can introduce your own work. Good. Well, that's interesting. Maybe yeah, let's hands up. You mean? Okay, 1, 2, 3, 4. Okay, 5. Okay, so 1, 2, 3. Hands up. Yeah, hands up. Yeah. Maybe yeah, you mean can order the thing, and then you can have a meeting together. Good. Okay. Then let's thank the speaker.
네, 제가 말씀드릴게요.
네, 그러면